Introduction. I'm glad to be here. My name is Huaijin Chen. I go by George. I am an assistant professor at the ICS department. Today, I would like to talk to you about how we'll be able to build computational cameras for 3D imaging by leveraging the power of AI and optics. Okay, so before we start, a little bit about myself. I am an assistant professor at UH Manoa. I did my PhD at Rice University, majoring in ECE, and my undergraduate at RIT. I graduated with a Bachelor of Science in Imaging Science. Before joining UH, I spent a couple of years in industry working at various companies, ranging from small startup to big tech. So for today's talk, here's the outline for today's talk. I will first to give you guys some overview of computer vision and computational cameras. The two essential questions I want to sort of start off are why is camera important to AI and computer vision, and how we will be able to advance AI and computer vision with new computational cameras. With that in mind, we'll get into some kind of a background introduction on 3D camera technologies. Even though computational cameras can be very powerful in doing a lot of tasks, for today's talk, we'll be focusing on using the computational camera to sense 3D. And after the overview, I will go over two of my work in the field. One is on transient imaging. I will get to what transient imaging is in a bit, and then time-of-flight depth sensing. And after that, I will talk about another paper I did where I was in grad school, which is using AI to jointly design optics and 3D sensing algorithms with AI and perform single-shot passive depth imaging. And lastly, we will actually have a very exciting hands-on demo with the AI-powered monocular 3D cameras. So if you want to actually follow me and then do this demo, you will need to actually have a computer with the NVIDIA GPU. And then we will just walk through how you will be able to turn your webcam actually into a monocular depth sensing camera. Okay, so here's the outline. So let's get started. So over the last decades, we have seen amazing advancement in computer vision. We are now able to generate fantastic artworks with just a sentence, or make car drive themselves or drive safer with the visual tracking and semantic scene parsing. Or we can capture professional grade photos and then have immersive experience with the AR and VR. So the natural question is how we got to this point. I think now we can all agree the large-scale data set and machine learning directly contributed to this computer vision revolution. We have large imagery data sets with over 1 billion labeled images and powerful GPUs providing the computing power needed for the task for training and inferencing billion parameter neural networks or AI architectures. But if we trace back further behind the scene, at the core, such revolutions are relying on one single revolution that happened in the last couple of decades, which is the camera revolution. Because without cameras, we have no input data to work with. We will have no input data to work with for pretty much all computer vision problems, right? So what has been happening with cameras? Two things. One, they got smaller, cheaper, and were embedded in virtually every smartphone that everyone is using every day. Secondly, the shipment of cameras, thanks to the wide availability of a smartphone and point-and-shoot digital cameras, has exploded. Right. Here I am plotting the camera shipments across the last 50 years, and you can clearly see the trend here. So from 2000 to 2021, the wide availability of the cameras drove the need for online public photo sharing services, which provides a good amount of imagery data for training computer vision models. So around the same time, visual computing advancements such as GPUs provides good means to process those imagery data. Together, they sort of formed a perfect storm to spike tremendous development in data-driven computer vision in machine learning. So by 2012, we had more than 6 million, right? So the shipment of cameras by that time, we have more than 600, sorry, not 6 million, but 600 million cameras out there capturing suitable training data for computer vision every day. So right about that time, large-scale data-driven computer vision sort of had its first win. As AlexNet, you probably have heard of the name, achieves unprecedented performance in image recognition tasks in a kind of famous image recognition competition called ImageNet. And the performance level of AlexNet is very close to human at that time for the first time. So the chart stops at 2016, but you could extrapolate the number, right? So today, large AI content generation model achieve unbelievable results. Behind the scene, it is trained on billions of images. And the state of our 5 billion image data set is only possible because billions of cameras in everyone's hand taking photos every day. So in some ways, you can argue that the low cost and easy to use cameras are the fundamental contributing factors to AI and computer vision success. So looking into the future, what are the next chapter for computer vision? If we can call the current state of art of a computer vision as computer vision 1.0, what are the challenges for computer vision 1.0, and what can we do and what can cameras do for computer vision 2.0? That's the questions I hope to partially answer in today's talk. So indeed, camera revolution from the bulky DSLR camera to smartphone cameras is definitely reshaping the landscape of computer vision 1.0. However, most of consumer cameras nowadays still capture only the intensity of a light in 2D, right? You basically are capturing the 3D projection of the world onto a 2D camera plane. So so which is not too different from the first camera obscura or so-called pinhole camera invented centuries ago. At the system level, cameras is still designed separately from the downstream computer vision algorithms or AI algorithms. Most of camera makers aim to improve the optics to capture perfect images for human viewing still, right? But from signal processing's perspective, this is like constructing an identity matrix to sample the world. Right? But we have to keep in mind that optics has its limitation, right? It has its physical limitation, right? Building a perfect lens requires you to do tremendous engineering around the optical system. And a lot of time building a perfect imaging system that mimics the identity matrix is very difficult. And more importantly, right, downstream CV tasks, computer vision tasks, don't always need eye-catching photos in the AI era. So as you can see, right, this kind of creates a mismatch between the camera we build and the algorithms or the AI models we develop. Thirdly, high computing need is another challenge of current day computer vision system. Training a single 200 million parameter transformer network, which by today's standard is actually pretty small, will requires 300 more carbon footprints than a round trip flight between Hawaii to mainland. And then lastly, most of the existing computer vision data sets, especially for high-level computer vision tasks, relies on manual labeling. Manual labeling is a tedious task and may not be able to apply to new imaging modality, right? If you're sensing something that human cannot nicely perceive, right, it will be very difficult for you to actually label the data set of a new imaging modality, right? On top of that, the pure data-driven nature of most of the neural networks or AI models means that a model is a black box. While it might be okay to use a black box to tell a cat from a dog for entertainment purpose, or maybe generate some cartoonish rendering for your photos, right? It may not be, certainly it's not favorable in many mission critical scenarios, such as self-driving cars or healthcare applications. So for computer vision 2.0, I believe camera should be able to capture not only the visible 2D intensity, but more properties in the so-called plan-optic function. So for those who of you haven't heard of a plan-optic function, it is a function that describes all the information about incoming light available to an observer at any given point in space and time. So properties like polarization, phase, wavelengths, beyond the visible spectrum, or time beyond the sensible time scale, future camera should be able to capture all those information at the low cost. And those cameras should be as easy to use as today's smartphone cameras. And then at the system level, for next generation computer vision, with computational cameras, we no longer aim to perhaps design a camera directly to directly capture the perfect photos, but rather we design cameras that capture more information about the scene through optical encoding and digital reconstruction. In this way, the raw sensor signal may not be directly interpretable by human, but they can more easily be used by the downstream algorithms, especially the AI models. Moreover, when you build this system using differentiable AI frameworks, we will also be able to perform AI-based end-to-end joint optimization of a camera optical system and the downstream computer vision algorithm through backpropagation. As a result, we should be able to build system that is optimized for a very specific task, rather than just building systems that captures eye-catching photos. So on the computing power side, with the task-specific design principle in mind, we can design cameras that can efficiently sense information that's only relevant to your task. And at the same time, we can offload some neural network computing through optical computation, because some certain computation that we perform nowadays is significantly more efficient in optics than in electronics. One good example will be convolution, right? Pretty much convolution is the fundamental building blocks for modern computer vision neural networks. In optics, if you want to perform convolution, it's pretty much purely free because optics by nature is performing convolution there. So we should be able to offload some of the computing to optics for you to save computing power. And lastly, by leveraging imaging physics, we can enable self-supervised learning to reduce the need for labeled data. And by introduce physics-based layer or loss in the neural network design, we can make neural networks more interpretable and more dependable. And more importantly, have a physics grounding. Or when online self-supervision is not desirable, we can also use physics-based rendering to generate a large-scale data set. This is an important source of training data when real-world ground truth data is hard to capture, such as imaging novel light modalities, such as this transient imaging case I'm showing. So putting all the pieces together, I believe we now have a very good blueprint for the computer vision 2.0 endeavor. So while I'm listing several research I've done previously on this map, for today specifically, I will talk about building cameras that can capture more information about light in the form of a 3D. 3D information such as depth and phase of the light. So first of all, let's have a quick overview of 3D cameras. We can sort of categorize 3D cameras, current day 3D cameras, into two categories. One is active 3D cameras, and the other is passive 3D cameras. So under the active 3D camera category, you will have a camera and an active light source. So under this category, you have techniques called the structured light, time of flight, or maybe you have heard of the word LiDAR, which stands for light detection and ranging, right? So this is based on the principle of a time of flight, which we'll get into in a bit. And you can also perform photometric stereo if you have multiple light sources in a static scene. So under passive 3D sensing side, you have a stereo camera setup where you use two cameras to triangulate the depth within the scene. And you can more recently have monocular depth estimation, which we will show a demo at the end of the talk. And certain optics will also encode the depth information in very interesting form, such as focusing and defocusing. It actually tells you some information about depth within the scene. And you can also have this kind of a very interesting camera called the light field camera, which will capture a lot of more information about light. And if you have a polarization camera, the polarization filters you put in front of a camera also will provide some information about the 3D geometry. So let's take a look at some of those camera technologies. So on the active depth sensing side, for structured light, you will have a projector that will project some certain patterns onto the scene. And this pattern from your projector will be distorted because of a 3D structure of your object in the scene. And your camera will be able to measure this resulting patterns. And depending on the distortion, you will be able to reconstruct the scene 3D. And one of the famous example for this structured light will be the first generation Microsoft Kinect, which is a input device on the Xbox gaming system. For this camera, it basically does the structured light in infrared. So you don't actually see this patterns in your in human vision, but it will project IR patterns like this to the scene, and then it will have a camera that capture the IR patterns observe the IR patterns and then calculate for the depth. And then you can use that for interaction. And on the time of flight side, the principle is quite straightforward. You have a laser right next to a camera. You shoot out a laser to the scene, to your target. The photon will hit the target and then return back to your camera. Since you know the speed of light, if you can know how long it takes for the light to be emitted, hit the target, and then get back to your camera, in that way, since you know the speed of the light, you can calculate for the distance. Right. So based on this principle of the time of flight cameras, there are several kind of product you can see on the market that performs depth sensing. One example will be the second generation Kinect, which was released in 2014. And a newer iPad or iPhone also has this LiDAR scanners embedded in the camera modules. And if you have ever taken this self-driving cars, you will probably notice this very kind of a signature look on top of each self-driving car's rooftop. This is actually a LiDAR. So yeah, basically all those products you see on the market operates on the principle of a time of flight 3D sensing. Okay, so and then, as I mentioned, you can also have a photometric stereo where you have a fixed camera and fixed object, and then you will have a point light source that light up the object at a different angles. And depending on the appearance of the resulting captured object, you will be able to infer the 3D shape of the given object. And then on the passive sensing side, one classic method you will use are this kind of a stereo camera setup. So you will sort of observe the same target from two parallelly laid out cameras. And then if you know the camera geometry, like essentially what the focal length of the camera and the physical distance between these two cameras, then you will be, and if you can know also the corresponding points within each camera's image plane, then you will be able to use triangulations to calculate for the 3D position of a given point within your 3D scene. So on this line, you have a commercial products such as Intel RealSense and the Z camera from Z Lab that will do this passive 3D sensing through stereo camera. And also more recently, you have monocular depth estimation. So usually those type of methods are data-driven. Just like human, if you close an eye, if you close one of your eye, right, you should still be able to tell the scene depth, because there are other sort of a depth cue that's within your scene that can help you to do this 3D sensing, right? So for example, the occlusion of the different objects, relative size of the different objects, shadows, shadings, textures, and perspective, those are all gonna give you some depth cue, right? So that you can infer the depth within the scene. So similarly, you can train neural networks. You can train AI to try to extract those depth cues within the scene and then estimate the depth given the image. So to do that, you usually have a network, right? And then you will need to train the network with a lot of pairwise data with input RGB color image and output ground truth depth, right? You let the network to see hundreds of millions images, image pairs of input image and ground truth depths, then eventually you will be able to predict the depth when you give it a RGB color image that it didn't see in the training. right? To do that, you will need to have a lot of training data, right? So here are some examples of a popular training data for monocular depth estimation. So Kitty is more focusing on the self-driving car scenario where it has a car-mounted camera that captures the photo of the cars driving around the city. And meanwhile, it has a LiDAR that captures the ground truth data. And then you also have a ETH3D. Similarly, it has a laser scanner, which works with the same principle of a time of flight, right? Generating this high resolution 3D maps. And then you also have NYU Depth V2, which is indoor color image, as well as the ground truth depths. In the NYU depth data set, the ground truth data are captured using Connect, first generation of a Connect. So those are all real world 3D data. At the same time, you can also have synthetic data, such as the flying things 3D, right? So the good thing about synthetic data is that you are able to actually generate a lot of data without painstakingly curated this kind of pairwise image. As long as you can do computer graphics rendering, then you will have a lot of training data for that, where you have input image and then underlying depth. Right, and then you can generate a lot of random scenes and the corresponding ground truth depths corresponding to the random images. Okay, so that's on the passive sensing monocular depth estimation side. So as I mentioned, there are also other depth cues, right? So one thing is the depth from defocusing or focusing, right? So if you have done photography before, you will know that the blurriness or the sharpness of a given pixel or given pixel patch, it actually carries information about the depth, right? So you can computationally measure the blurriness or the sharpness of your pixels. In that way, you will be able to get the depth. And then we also talked about mentioned about the light field camera. So for the special thing about light field cameras is that instead of having just a lens and a sensor, in front of a sensor, it has a specialized lenslet array, which will not only tell you, so for normal camera, you only measure the 2D intensity of a light at a given pixel location. But for light field camera, instead of just the 2D intensity, you also have the direction of each light ray that come into your main lens. So in that way, you can capture the whole sort of a light field, and then that will allow you to do a lot of cool stuff, such as post-capture refocusing and post-capture view angle changing, right? So then your depth information can be extracted from this post-processing as well. And another formulation of a light field camera will simply be just have an array of a camera, right? In that way, you can also sort of get the information about where the light ray is coming from, besides just the normal intensity of the light. Okay. And lastly, on the passive depth sensing side, you also have shape from polarization. As you probably have done photography before, right? So some people will put a polarization filter in front of a camera, which allows them to actually enhance the color or allows you to actually reduce the reflection, right? So polarization actually carries information about the 3D geometry of a surface, because reflected light and transmitted light will have a different polarization. Quantitatively, we can characterize those polarization by two parameters. One is called angle of a polarization, and the other is called the degree of a polarization. So with these two property there, the angle of a polarization and the degree of a polarization, you will be able to actually estimate the surface geometry. And in that way, you will be able to infer the embedded 3D information within your scene. So for photography, traditionally, you will probably capture multiple images while rotating this polarization filter. But nowadays, Sony and some other sensor manufacturers, they have this kind of a per pixel polarization filter embedded in their sensor. So with a single shot, you will be able to capture the full angle of polarization and degree of polarization to help you to get the depth information or the 3D geometry from the scene much more easily. Okay, so that's pretty much for the overview. Next, I would like to dive deeper into two of my work. Before we do that, is there any question regarding the overview we have done so far? Okay, so if not, we will move on. Okay, so the first thing I will like to cover is so let's start with seeing the unseen with the help of computational camera and physics-based renderings, and how we can use the principle, such a principle to build low-cost depth cameras that has improved depth accuracy. Okay, so the first work I will go over is ITOF to DTOF. So in this work, I've done at the SenseBrain, we use a low-cost time-of-flight sensor to achieve transient imaging and depth estimation. I want to acknowledge that I was very grateful to mentor a very brilliant intern, Felipe Gutierrez Barragan, on this project. And then we had the work published at IEEE Transaction and Computational Imaging. So what if you can see light in motion? That's essentially the purpose of doing transient imaging, right? So with computational imaging, you can actually do that. So on the left, this is one of the first transient imaging results. Right. So here, femtosecond level light transportation is recorded. So you can see the laser shoots the light pulse into the bottle. The light pulse scattered in the solution, and then the light pulse hits the cap and then bounces back. Right. So to achieve this result, you will have to use a street camera and a femtosecond laser to construct a direct time-of-flight or so-called DTOF imaging system, which I will cover just in a second. So to get this result here, it will actually take you a full day to perform the repeated capture to reconstruct this video, because for each single capture, since we are recording something at the single photon level, right? The signal to noise ratio will just be too low to just get the meaningful signal there to get this video. So what you have done is you shoot out the laser pulse at the same objects again and again, right? So every time it will go through this deterministic repeating process, right? So over millions of captures of the same movement, you can average over all the frames. And then in that way, you will be able to get a more meaningful light transportation video like this. Okay, so that's how a transient imaging or DTOF imaging will work, right? So 6 years later, when we start this project, we had a low-cost indirect time-of-flight sensor from Sony. We will get into what indirect and direct time-of-flight differ in a bit. But the goal is to see whether we can achieve a similar result with a much cheaper sensor, given the technology that it is available, like AI-based algorithms, as well as cheaper indirect time-of-flight sensors, whether we can achieve this kind of a transient image results. As you can see here on this video, we sort of roughly were able to achieve it. So to to understand, yeah, so and then we are able to achieve it at the fraction of the cost, right? So this whole thing costs less than just $10, right? So to understand how this works, let's first take a look into the principle of the time-of-flight camera, right? So direct time-of-flight imaging system, or DTOF system, are composed of a sensor and a pulsed lasers that illuminates the scene, right? The laser will illuminate light pulse and measure the returned signal with the sensor. So each DTOF pixels will encode the depths in the time delay between the immediate pulse and the received signal, right? So for a given scene, to measure the round trip time of the pulse, the time-of-flight DTOF system uses ultra-fast sensors that capture the video of the light pulses as it propagates through the scene at each pixels, right? So at each pixel level, you will have an immediate pulse, and then you have a return pulse like this, right? So then the time delay between these two pulses, the immediate pulse and the receiver pulse, will give you the depth of that given point, right? And then if you repeat this process, so the depth is encoded in this time delay, and the light propagation is encoded in the whole return signal, right? So we do this for every pixel within the scene. And then we will be able to generate a video like this. And this videos those videos are referred to as the transient imaging, or transient image, or DTOF, direct TOF image. Any questions so far regarding DTOF imaging? That's basically how LiDAR works. Okay. If there's no question, let's get into iToF, right? So the hardware cost of a DTOF sensor is very high, as you will need to operate at pico or femtosecond regime, depending on the scale of the scenes you are imaging. A different modality of a time-of-flight imaging is called indirect time-flight, or iToF. So iToF system will similarly illuminate the scene, but instead of a pulse, as we have seen before, this time it will illuminate the scene with a sinusoidally modulated light pulse, right? So before we have a super fast light pulse, right? It's just shoot, and then there's a light pulse. But now we have iToF signal instead of a pulse. What we have is a slowly changing kind of sinusoidal signal. So it goes from bright to dark with a relatively more time, right? So it's not a pulse anymore. It's basically a sinusoidal wave, right? Then what we hope to measure is essentially the shifts of the same sinusoidal wave signal received by the sensor, right? So then your depth information will be encoded in this kind of phase shift. So how do you get those phase shift, right? So the phase shift, instead of relying on ultra-fast sensor to measure this phase shift, iToF camera correlates the receiver signal with a known sinusoidal signal at the same frequency, right? So as a result, you will be able to get this kind of a correlation signal. So if you repeat this process so this is what the single pixel is doing, right? So if you repeat this process for every pixels within your camera, then you will be able to get this kind of correlation image. Then you can get another correlation results with a different reference signals with some phase shift, right? So in that way, you can inversely solve for the phase shift. So since there are three parameters that defines a sinusoidal function, right? So you will at least repeat this measurement 3 times, right? With the 3 different reference signals. and then you can compute the phase shift to receive the signal and extract the depth. So in that way, you will, so usually for iToF's camera, instead of just having one frequency, you usually do it with maybe two frequency, one of a higher frequency and one with a lower frequency. Okay, and then you will be able to actually get this kind of a transient image, and you can back calculate the phase shift at each pixel location, and the phase shift there will be able to tell you about the depth. But in this cases, you don't actually get the transient because you don't actually have this impulse response in your system. Any questions so far on iToF and DToF cameras? Okay, so if no other questions regarding iToF to DToF, I will move on. Right. So there are a lot of there's a lot of strengths about the iToF cameras. They're usually lower cost because you no longer need those high fast lasers and fast sensors, right? And then they are usually of a much higher resolution than the direct ToF LiDAR. You can easily get 1 megapixel nowadays. And the form factor is much smaller, and it can be made solid state, meaning unlike the spinning LiDARs, right, you don't have any moving parts. So as a result, you have a lot of interesting 3D applications such as AR, VR on your smartphone or sensors on robots, right? But iToF sensor faces important challenges. First, those cameras often operate in low SNR settings due to practical constraints such as low power and low exposure time because you are operating it on the sensor, on the smartphone, right? Secondly, they suffer from a so-called multipath interference, which is caused by indirect light paths hitting the sensor, right? Imagine you have in a DToF case, right? So you shoot out a photon. The photon hits the target. What you want to have is the direct bounce back photon, right? But what can also happen is that photon might hit your target and might not directly come back to your sensor, but instead it kind of maybe hit some objects. Maybe think of a wall or something, right? A corner of a wall. Then it will hit the another side of a wall and then bounce back to your sensor. So the captured signal on your sensor is not the first bounce, right? It might be the second bounce light, right? So for a DToF sensor, there might be a way that you can get around with it if you have the full kind of impulse response function, right? So if you can just find the first peak over there, then you still know that the depth, the actual depth there. But for DToF sensor, as you can see here, right, you won't be able to actually recover. So the recovered sort of a phase shift at this point is kind of be impacted by the second bounce or even more bounce signal, right? So yeah, so in the presence of an MPI, multipath interference, this phase shift of a returned sinusoid will not only depend on the direct reflection, but also dependent on multiple indirect reflection, right? So we can see that the depth you were able to resolve is actually shifted from the actual depth of the scene. Okay, so traditionally, one common approach to overcome these challenges is to first denoise the iToF image and remove the MPI. To remove the MPI, many solutions have been proposed. Many of them have do involve estimating the transient as an intermediate step, right? So once you have the transient, then you can pick the corresponding peak within your impulse response function and then get the depth, right? But most of the traditional transient estimation methods work only in simple scenes in lab settings. And then you have to impose a lot of assumptions sometimes unrealistic assumption in order to solve for this inverse problem. For example, this method, right, it just assumed that you will only have up to 3 kind of returns within your scene, which is definitely not the case, right? And also it kind of impose an assumption about the return signal's shape, which is also much more unconstrained in the real world cases. And more recently, there are network or AI-based method to resolve this problem, right? So we kind of group this kind of a data-driven pipeline to resolve the MPI issues into 2 categories. One is depth to depth, and the other is ITOF to depth, right? So for depth to depth model, you pre-compute the MPI corrupted depth regardless, and use them as input to the data-driven neural network or AI to produce the MPI-free depth, right? And on the other hand side, for ITOF to depth, you kind of skip this kind of a intermediate step. You directly input the raw ITOF image into the network and produce the depth map, right? Here you can see that both of the methods require you to have a ground truth depth for supervised training of such a network. Right. So due to the dataset limitations, those data-driven ITOF models don't explicitly estimate the transient response of the scene because the training data doesn't have this kind of a pairwise data between DTOF and ITOF, right? So sometimes it's challenging to actually provide the correct depth for supervision, right? So in a scene with a diffuse MPI, the correct depth is usually encoded in the maximum peak of the returned transient signal, right? But in the presence of a semi-specular surfaces, like a glossy floor in the scene, the correct depth is included in this first peak rather than the maximum peak. So yeah. And then there are also cases, so-called optical crosstalk, right? Say if you have a high contrast object, and then in those cases, if it's very high contrast, it might be able to leak the light into the background region. As a result, you sort of have this kind of corrupted depth estimation. And then there are also cases at the depth boundary or depth discontinuity, right? So those pixels could either belong to, this boundary pixels could either belong to a foreground or belong to the background, right? So in that case, half a pixel might be covered by the foreground object and half a pixel might be covered by the background object. So in that case, it's difficult to tell what is the actual ground truth depth in those cases. So as you can see, performing the depth supervision without transient for all this scenario could be challenging and sometimes more ambiguous. Okay, so that's why we kind of proposed this framework called ITOF to DTOF, right? Like the previous data-driven ITOF models, we begin with the captured ITOF frequency data, which are the correlation measurements over several low frequencies. And the data is then fed into a data-driven model. Instead of predicting the depth directly, our model actually interpolates and extrapolates the ITOF signal data, frequency data. And then we basically kind of calculate for the dense frequency representation that is used to estimate the DTOF image. Particularly, we use inverse Fourier transform across the time domain and perform filtering on top of that. And then, so at this stage, you will be able to actually get the transient image out of your ITOF capture, ITOF input. And then once you have the transient image is already pretty good results that will give you some information about the light transportation. And about beyond that, with the transient image, you will be able to estimate the depth by using rule-based peak finding algorithms. And depending on what kind of scenarios you have the flexibility to actually estimate the depth within the scene. Okay, so that's the overall kind of overview of our proposed method. So in order to achieve that goal, we actually need to build a state-of-art data set, which previously didn't exist, of pairwise the iToF and dToF imaging data, which with the physics-based rendering. So so in our data set, this iToF and dToF pairwise data actually contains about 1.5 billion transient impulse response function and iToF frequency measurements data across a wide range of frequency from 20 to 600 megahertz. And we also developed some peak finding script to decode the depth depending on your applications. And for the synthetic data we generated, we carefully modeled the actual iToF sensors power and noise specs to reflect that in our synthetic data set. As you can see, compared our synthetically generated data versus the real data, though they are actually pretty similar. And so here is one result of the estimated transient image, right? The scene actually of my living room back in the COVID time, because we don't have access to the lab. So this scene kind of exhibit specular reflections on the television, which will lead to a low amplitude direct kind of a reflection component, as you can see in the recovered transient pixel, right? So if you don't have this transient output, right, so you might likely to get an incorrect depth estimated for that point. But with our sort of intermediate estimated transient pixels, you are able to actually pick the low amplitude direct reflection and then use that as your depth results, right? So in the traditional method, because of specularity, you have incorrect depth estimation. And then with the previous data-driven method, you also have an incorrect depth estimation. But in our case, we will be able to kind of perform the correct depth estimation over those challenging specular pixels. Here is another example of the optical crosstalk I mentioned before, right? So because of the strong foreground lights kind of leaking into the adjacent area, with the traditional method, you will be acquiring those incorrect depth output. But with our method, you will be able to pick the correct peak for estimating the depth, and then you will get much more clean, less corrupted depth. Okay, so and then here are more real-world example of our method compared to the traditional method, and overall we achieve less of a MPI while getting overall pretty good depth estimation. Okay, so in summaries, we have proposed in this work, we have proposed a robust and flexible framework for data-driven iToF imaging that outputs the transient response and the MPI-free depth map. And we also, in order to achieve that goal, we provide a state-of-art large-scale data set with multiple frequency iToF measurements and dToF transient impulse response ground truths. And we have done extensive study on the validation on the Sim2Real comparison. So the code is actually available if you want to give it a try. Okay. Any questions so far regarding the time of flight sensors and our work on iToF to dToF? Okay. If not, we will have a deep dive into a second work I would like to present today, which is so-called FaceCam 3D. So at a high level, this work, there are two key novelties from this work. One is that we proposed an end-to-end AI learning framework for optics design. So the AI learning framework will be able to design both your optics and the digital reconstruction network to give you an end-to-end optical system that is optimized for depth estimation, right? So another novelty here is actually we have shown a actual prototype system for passive monocular depth estimation, which achieves a state-of-the-art performance. In our monocular depth estimation, we actually have some hardware modification optimized, designed by the AI to put on top of a lens to help you to better estimate the depth. I will go into the detail. So for this, it's basically tackling these 3 points on the landscape, on the blueprint you have seen before: system design, model data, model and data, and then some optical computation. Okay, so in my previous work, I've done a lot of work on incorporating imaging physics along with deep learning. But for this work, let's first look at the end-to-end design aspect. So this work was done in collaboration with my collaborators at Carnegie Mellon University. So the motivation, as I mentioned, is to perform single view, single shot, passive 3D sensing. So why passive 3D sensing? It will be robust to environment, and it will require lower energy because you don't have an active light source, and hopefully it will be lower cost. And why do you want to do single view and a single shot? Because you don't have an occlusion problem there, since you don't have a co-located camera or co-located laser there. And given that it is a single shot, you can deal with a dynamic scene. So on the underlying principle for this proposed design is related to the depth from defocusing, right? As I mentioned before, if you have done photography, so you've probably heard of a term called like a bokeh or depth of field, right? So essentially, in focus object will be sharp, and out of focus object beyond some distance will be blurry, right? Depending on how blurry or how sharp you have at a given pixel, you can infer the sort of the depth, right? So basically, what I'm showing to the bottom here is our so-called point spread function, right? So for in focus a point within the scene will still be mapped to a point on your image plane. As a result, you will have very clear, sharp pixels. But for the out of focus points, right, a point within the scene will become the point will spread to a larger blur circle, right? So as a result, you will have a very kind of a blurry image, blurry appearance at those out of focus locations. But as you can see, the problem is that there's an ambiguity of a near out of focus and a far out of focus, right? Essentially, the nearby objects might be blurred in the same way as a far away object, right? So in order to solve this ambiguity problem, people have done previous work on this topic by adding some coded mask at the aperture plane, right? So that your point spread function will no longer be this kind of symmetrical, right? So for near out of focus and far out of focus, if you can introduce different type of a blur that are very different from each other, then you will be able to infer the depth better, right? So previous work have shown using amplitude mask to achieve this kind of special type of PSF that will that's very depth dependent, right? So our work on top of that do not use amplitude mask, because amplitude mask can, as you can see here, will block light. As a result, your light throughput will be lower and you will have a higher noise, right? So we will actually preserve more light by not using this amplitude mask, but rather a phase mask. And previously, finding the best pattern that can achieve this kind of depth-dependent PSF is done manually. But in our case, we have a AI optimized coding design, phase mask coding design that will optimize the variability in the PSF, depth-dependent PSF. So there is some other previous work in the space of end-to-end optimized optics, right? But they are tackling different problems of doing, for example, in this case, doing extended depth of field, which aims to make the PSF as small as possible across the depth, so that you will get a all-in-sharp image after neural network reconstruction. And there are also some other works on phase estimation, phase mask for depth estimation, but previously they're not done in an end-to-end fashion. They basically still design optics and then use a network to sort of decode the depth from the image. So in our work, right, as you can see, we make it truly end-to-end. We have optical layer which simulates the optical process of the phase mask at aperture plane. Essentially, you can think that as a differentiable simulator, physics-based simulator of how a phase mask will affect your final image, depending on your original input as well as the depth of your scene. By introduce this phase mask, you will have a PSF, very different PSF, after the optimization, different PSF across different depths, right? So that will be the optical part of our AI framework. And then this will give us a realistic rendering of what the real world optics will look like if you have such a system of such a phase mask applied to it. And then once you get this image, your goal is to extract the depth information from this image. And to do this reconstruction work, we have a depth reconstruction network that will take in this coded image and estimated depth. So at the training time, we actually optimize for both, right? So the goal is to first have optimize the depth estimation, depth map. And secondly, you are jointly optimizing this optical component so that it will optically kind of extract as more information about the depth as possible in your coded image. So after the training is done, we will actually manufacture the optics according to the AI's optimization results and put that physical optics on your camera system and then capture image like this, right? So you're in the inference time, you will start with this part, and all this part of optical computing is done in the optical domain, right? And then you will basically just run the image through the depth estimation network we previously trained, and you will get a estimation depth network. Estimated depth result, right? So here is the optimize the face mask. Essentially, you will have this kind of a different height at the different location of that face mask. As a result, this shape will actually give you a pretty interesting PSF across different depths, right? As you can see, compared to previous case we have seen for the depth from defocusing case, where the PSF looks very similar on the far end or on the near end. In our case, the PSF for the far end and the near end are very different. So in that way, you will be able to get very differently blurred image depending on image patches, depending on their depth within the scene, right? So after we optimize this design using AI, we actually use this kind of a 3D printer, a nanoscale 3D printer to print out the face mask. And then we place this face mask onto our existing camera lens. And then you essentially construct a face mask-based depth sensing system. And then, so you will be able to run your optics in real world and then get the estimated depth in real world. Okay, so here are some simulated results from our system. As you can see, it kind of give you a pretty similar result to the actual ground truth depth. And we also, more excitingly, have very good real world results where you are able to get the depth quite nicely with all the kind of a detailed structure preserved. And when you have this kind of a texture, but a flat surface, you will actually, your network won't be fooled by the texture, but still be able to give you this kind of a correct depth estimation. Okay, so, and lastly, for real world results, we compare our results with the commercial Kinect depth sensor. As you can see, our measured depth from our camera is quite close to the measured depth from the ground truth Kinect camera. And then we also perform this kind of a benchmark study using the NYU depth V2 data set. And you can see that we are achieving pretty good results compared to all the previous results. But I must say, even though on the number, we're much better off, because here the rooming square error should be as small as possible. The smaller, the better, right? But we have to mention that for all the other monocular depth estimation, they did it without additional optics, like the face mask we introduced. But in our case, we did have extra piece of hardware. So it's not a surprise that we achieved better results than the previous monocular depth estimation result. Okay, so that's pretty much for the iToF to DToF, FaceCam 3D work we have done. So as I mentioned, right, two takeaway. So one is that you now can actually design end-to-end deep learning or AI framework that allows you to optimize everything along your image pipeline, no matter it is the physical optics or your downstream CV computer vision networks, right? And using this principle, we're able to actually design and fabricate a passive mono-depth monocular depth estimation sensor, which achieve state-of-the-art depth sensing performance. Okay, so with that, I have done with my to deep dive into my previous work. But looking into the future, I hope to kind of expand into computational. So with this kind of new imaging sensors, right? I hope to expand into using computational imaging, new computational imaging device for robotics application. Some of my previous work I've done at a startup was essentially using polarization-based stereo camera to perform depth sensing with a much higher depth density, but only at a fraction of the cost, right? So as you can see, there are small transparent objects which are invisible in the normal camera, but with the polarization, you will be able to pick out those objects and then perform depth sensing with the polarization plus the stereo, right? So this is a LiDAR's performance, which will cost a fortune, right? The cheapest LiDAR will probably be around $1,000 or like a $700, right? The depth map is actually quite sparse. But with what we have built at Value Robotics, right, as you can see, the depth density is really high. And you are also able to capture those ultra small objects within the scene. So for the company, we were actually equipping this kind of a computational imaging device onto those self-driving delivery robots so that we can achieve a low-cost robot. We can build a low-cost robot with this kind of a novel optics that can perform depth perception tasks. This is a significant saving because LiDAR used to be one of the most expensive sensors on self-driving cars. By utilizing computational imaging technique, we were able to sort of achieve even better depth quality than the LiDAR at a fraction of the cost. So that will be one of the applications of a computational imaging on robotics. And the other kind of a line of work I'm currently doing is using computational imaging for agricultural robots. I am actually currently leading a team of a student to participate in this farm robotics challenge. In particular, we were using multispectral camera to have better reconstruction of the Dole pineapple field and the flower detection of the Dole pineapple field, which currently the scheduling of the harvesting is a pain point. But by using computational imaging technique there, we can have better estimation of the harvested timing so that people can schedule more accordingly, saving a lot of a cost. I'm also collaborating with my collaborators at Hilo and NYU to actually equip underwater robots with computational cameras, so we can do this kind of aquaculture more efficiently with improved depth sensing, fish tracking, vision-based depth sensing and fish tracking algorithms. And lastly, I want to make a small, on this line, on the imaging for robotics line, I want to make a small announcement. My lab is currently co-organizing a robot picking challenge, visual perception-based robot beam picking challenge, where given multimodality image input, including the normal image, polarization, as well as IR dot projection input. The goal is to predict the pose of each object. And then so that the robot arm will be able to pick up the object accordingly. So we are organizing this along with Google and then Intrinsic, which is the industrial robot arm of industrial robot branch of Google or Alphabet company, as well as OpenCV. We're organizing this workshop and a beam picking challenge at this year's CVPR. And there's a total prize money of $60,000 that you can win for this competition. And then if you are working on visual language action model, I especially encourage you to try, because all the baseline model we have built so far are with the more traditional based kind of networks and the post-estimation technique. So if you're working on AI-based, let's say, visual language action model, please, there's a very good chance that you can actually win the competition. So I encourage your participation in this competition. And also on the imaging itself, I am working with my collaborators to actually develop future sensors that allows you to capture more properties of a light, such as the phase information. With that, Are my acknowledgement of my collaborator, which contributed to the work I've shown in this presentation. Also, my funding agency for my graduate study, NSF, Texture Instrument, and ONR. Here are the reference for all the works we have talked about. And all the works, the two works I presented today, all have code and data set available on my website. So make sure if you want to try it out, make sure you visit the website. Okay, with that, this is the end of the first phase, which is the lecture. I am actually looking for PhD students and collaborators to join my computational imaging or robotic perception lab. So maybe we will have a 1 minute break or maybe 3 minutes break. Then we will get into session 2, which is a mono depth demo. So for this demo, you can make sure if you want to actually try out this demo on your own computer, please go to this address to download the code as well as the model you will need for this demo. Okay, so we will come back in maybe 3 minutes. Shivani, can you give me access for screen share?
Sure.
I have another computer logged in. The name there is called George Demo PC.
Gotcha. Okay. Let me make you co-host. Can you try now?
Okay, let me see. Okay, so I will stop the sharing on the original computer. Okay. So, hello everyone. Welcome back. So for the second session, we will go through this depth demo. Okay. So a bit of a background, right? So we talked about monocular depth estimation, mostly in the context of my previous work of like phase mass-based monocular depth, which estimation, which will require you to have a specialized piece of a hardware, right? But as I mentioned, even without the special hardware, even with your single eye, right? If you look at the scene, you will still be able to kind of infer the relative depth within the scene. That is because you have a lot of cues regarding your depth, right? So the hope for some of the monocular depth estimation work is basically trying to train a network to let the network to be able to extract the depth information given a color or grayscale image input. So for today's work, we will try to run one of a state-of-the-art model depth or monocular depth estimation network called Distill Any Depth, which just came out in February this year, last month, on a laptop that hopefully you will have a laptop with NVIDIA GPU. So with this work, we will be able to fetch your. Oh, by the way, does anyone have access to the folder? So if you click on the link, which is this link here, go.hawaii.edu art8, small r, big R, and 8, that will guide you to this page. So you will have the slide deck for what I'm sharing right now. And then you will also have this code snippet for actually running the demo. Does everyone have access to that page? Actually, you know what? Let me make sure that is actually everyone has access. So, okay, so now you should all have the access. right? Just go to Shivani, maybe if possible, can you copy paste the link to the chat window so people can just click on it?
Yeah, sure thing.
Okay. So anyway, so the code is available in that folder. But overall, this is a new work that just came out last month. Uh, it kind of you might have already heard the word distillations in some recent large language model, right? So similar thing can be applied to this kind of molecular depth estimation task as well. Say if you have a pretty big network, teacher network that is pre-trained on a lot of the data, you can then train your student network based on the teacher's network's output. So this is essentially what this work is about, right? But you can actually see the result from this distillation actually is pretty awesome. Like you can get the fine depth estimation at those kind of small structure. And then for those actually pretty difficult case of like a dark environment, you can get pretty good results on all those scenarios. I choose this method because to demo today because it is actually the number one performing methods for the ETH3 benchmark on this. So if you haven't done too much of a machine learning, this is a quite useful website called Paper with Code. They run, I believe it's run by Meta Research, but it kind of automatically aggregates all those latest methods on multiple different machine learning applications. And they have a benchmark nicely kind of lay out on their website. So you can very easily tell which method is performing the best at the moment. Well, I guess I cannot access that, but yeah. But currently it is ranked number one, the method we're going to demo today. Okay, so some implementation detail of that method. It has a lighter weight neural network architecture based on this DPT, so-called dense prediction transformer. So if you don't know what the transformer is, here I gave a link, YouTube link on a very, very good explanation of what transformer is, right? And then the model is essentially distilled from multiple state-of-the-art teacher network, right? So the network architecture-wise, it has a transformer. So that DPT network has this transformer based setup, right? You basically, for a given RGB image, you break them down into different patches and then sort of embed each patch into a vector, right? And then this vector will be sent to a series cascading transformers. And then they also have this kind of a reassemble sort of a network building block that helps you to reassemble the output embeddings. And then through some fusion layers, it will kind of fuse all the transformers output and then combine them together and then form a output image, right? So at the training time, you basically have a pairwise the data. On one hand side, you have RGB image, and on the other hand side, you have ground truth data. And then you just basically perform this training by looking at millions of pairwise image. On one hand side, you have a color image, and on the other hand side, you have a depth image, right? So here is the screenshot from that paper, the distillation paper, how they were able to do this kind of distillation, right? So you basically fix the weights of the teacher network, which will generate the depth map on the fly or off a shelf. And then you have a student network kind of output something, but that student network is going to compare its output with the teacher network, right? And then the special thing about this setup is that they actually do this kind of a local global learning from the student to the teacher, right? So they were able to kind of use a lot of the teacher network, not a lot, but maybe several teacher network, and then let the student to learn from the teacher network and then get a combined result, right? So for today's demo, the instruction is pretty much like the following, right? So you will need to have a machine. So I have tested this on a Ubuntu 24.04 machine, and my current laptop has a mobile GPU, but it's already good enough for this network. So one thing about distillation is that you don't actually, so for the student network, it doesn't have to be a giant teacher network, right? So after the distillation, you can have a smaller network to sort of trying to achieve a similar performance as the teacher network. So this network is relatively small, so you are even be able to run it on the mobile RTX 4070 GPU in real time. Okay, so let's get started, right? So you will need to install Miniconda if you haven't, right? If you already installed it, let's just move to this line, right? So I will open up my window here. Can everyone see my screen, both sides? Okay, I assume all of you have can see my screen here. Okay, so I've already have done this environment setup, right? So if you, for you, you have to go through the setting up environment setup, set up a conda with the Python version equals to 3.10. And then we will need to activate this environment. So here, I already activate this environment here. And then I have already installed those dependencies. So if you haven't done so, please do it right now. It might take about a couple minutes because some of the packages are large, such as the Torch, PyTorch package here. Okay, so once you have done, then you can just look at the code, right? So, so this piece of a code is already nicely packaged into this transformer online repo. So if you don't know, so there is a website called Hugging Face. It's sort of the GitHub for all the AI models. They have a sort of a network zoo or network AI network collection, which resides in this package called transformer. So this is what we are mostly going to be used. So if you look at the original website, they have already done the heavy lifting there, that their model is ported inside the package. So we can just conveniently utilize this package here. Okay, any questions so far? Are you able to kind of follow through with all the commands here? Okay, so let's maybe go through this code base, right? So the pipeline is already sort of included inside this transformer pipeline library, right? So you basically just need to set up your pipeline, specifying the task as well as the model, right? So for this model, I'm basically getting this model using their instruction here on their website. And then the CV2 is the OpenCV package. Here we are only using, so OpenCV contains a lot of useful functions for all this computer vision tasks you want to do. Feature extraction, like image processing, 3D geometry, you can all use OpenCV. But for today, mostly OpenCV are traditional hardcore like non-deep learning, but in recent year, they incorporated some deep learning methods as well in their OpenCV library. But for today's demo, we'll only use this function in OpenCV that allows you to stream your webcam data. Okay, so here we set up the pipeline network. We set up the webcam capture using OpenCV, and then we will create a window, right? And then here, this is a helper function that turned a grayscale image into a color image so we can utilize it. Not that important. But here, what we do is actually we use the camera we set up to read the frames every time the webcam. So I have a while loop, right? So it keeps streaming whatever the camera is reading, your webcam is reading. And then you will have this camera data, image data packaged into the frame here, right? And then we show the frame, we show the frame along with the results there. Okay, so we will have, actually, this might be a extra line there that we don't need, but it's okay. And then we will have image, we'll decode the image from the webcam, and then we will put this image into the pipeline that we previously loaded, right? This monocular depth network. Then the output apparently is a dictionary, right? So then we just basically get this depth, try to get the value under this depth key, right? And then this will be our resulting depth, right? Then we will actually, let me just comment out this line before I forgot. Okay. And then, okay, so then after the depth will be shown in the resulting window. So here we are putting two images side by side. For the left, we have this original image, right? And then for the right, we kind of convert this depth from the network and then make it RGB image so we can see it in our OpenCV windows. And then we just basically show that, right? So that's basically the code, right? Maybe simpler than you thought because everything is already nicely packaged into this transformer library. But usually if that work is not done, then you have to actually do some work to pipeline your code. Okay. So anyone have any questions so far? Are you able to follow through? Any feedback from the audience? Okay, if not, maybe let's start running the demo. Okay, so all you need to do is make sure you have done all these prerequisites, and then you go to the folder that contains this code snippet, and then you make sure that your environment is actually activated, and then your environment actually have all those necessary kind of dependency installed. Okay, so let's start running this. Okay, so you have essentially built yourself a depth camera, right? So on the left-hand side, it is streaming your webcam, right? On the other hand side, this is this image going inside the depth estimation network and then give you this depth estimation output. As you can see, you get actually pretty detailed depth estimation, right? It can get this kind of a small structure such as my hair pretty nicely. I have a relative depth difference like this, right? You can clearly see this will have a nearer depth, median depth, and then background depth, right? So one thing you might have noticed is that we actually have sort of a flickering between the frame. That is because every frame, as you saw in the code, right, is handled individually. My group actually has a work submitted to this year's ICCV to try to generate static depth with the monocular depth estimation model. So yeah, so definitely that's some area people are actively working on. Okay, so with that, I think we are done with the demo here. Any questions so far? Are you able to get it to run? Okay, I guess not too much feedback from the audience. So yeah, but I guess, yeah, that's pretty much what I want to show today. Shivani, any other agenda?
No, that's great. Just wanted to say that's really cool.
Okay, okay.
Um,
To hear. Yeah, thank you so much. If you have time, please do fill out the survey. I believe Shivani already sent out or will be sent out a survey. Uh,
Thank
okay,
you, George.
thank you.
And thanks
Yeah,
everyone for joining us today. I did put a link to the survey in the chat. If you could take a few minutes to give us your feedback, that would be very much appreciated.
yeah, thank you so much.
It's
If
great.
you have any question, please feel free to reach out to me. And then I also have computer vision class and computational imaging class in the future semesters. Please considering taking if you found today's content interesting. Okay. Yeah, thank you so much. Bye.
Thank you.